Hi everybody, in lesson 6 here we're switching to looking at series, and a series is just a sum of a sequence. So I'm going to take a sequence and I'm going to add all the terms together. So let's look at this opening exercise here. Consider a geometric sequence where a1 equals 3 and the common ratio is 2. So my multiplier here is times 2. Find the sum of the first 7 terms. So let's find those 7 terms, and then we're going to find the sum of them. So 3 times ratio is 2, so 6, 12, 24, 48, 96, 192? Yes, 192. I'm checking that one. Yes, it is 192. So now I need to find the sum of these guys. I need to add all of those terms up. So on my calculator, I'm going to hit 3 plus 6 plus 12 plus 24 plus 48 plus 96 plus 192 is that sum equals 381. So a series is just when I take the terms of a sequence and I add them up. So a series, we use a capital letter S. S sub n is the sum of the first n terms. That's what this S sub n notation represents. I take a1, a2, a3, all the way up to a sub n, and I add those terms together. So that's what a series is. And we use this lovely notation here to represent it. So let's tackle what this crazy notation is here. This is the capital Greek letter sigma. It's the capital Greek letter sigma, and it means sum. Find the sum. When you see this big Greek symbol here, it means you're finding a sum. What's next to it is the explicit formula. That's what I'm finding the sum of. The bottom tells you where to start, and up top tells you where to stop. So the first thing I'm going to do is plug in n equals 1 into this formula. After I plug in a 1, I take a step up. What comes after 1? 2. I plug it into this formula. 3. Plug it into the formula. 4. Plug it into the formula. All the way until I plug in a 7, and I don't plug in an 8 because that upper bound tells me where to stop. So this is plug in a 1, plug in a 2, plug in a 3, plug in a 4, plug in a 5, plug in a 6, plug in a 7. Add all those things up, and that's what this series equals. That's what this sum, that's what this sigma notation is representing. So let's practice a couple of sigma notations here. So write out this sum here. So here's the formula, k squared. And we're indexing k where k equals 1. So I'm going to start by plugging in a 1. 1 squared. Now I did 1. Now I plug in a 2. 2 squared. Now I plug in a 3. I keep going. 4. I'm stopping here. Why am I stopping here? Because 5 is the upper bound of on that sigma there. So I'm going to do 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, and I get 55. That expression here is actually just the number 55. Sliding on over. Here, the explicit formula is just n. So I'm going to plug in n equals 1. Now I'm going to plug in a 2, 3, 4, 5, 6, 7. There's nothing really happening in this formula. We're just plugging in that number. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 is 28. This expression actually equals 28. That sum equals 28. That's how sigma notation works. You take this lower number and plug it in. So 2 times 0. I plugged in 0, so now I'm going to kick it up a notch, up to 1, up to 2, up to 3, 2 times 4. I'm just using that formula. 2 times 5, and then finally 2 times 6. I'm stopping at 6 because that's the upper bound of that sigma notation. 2 times 0. 0 plus 2 plus 4 plus 6 plus 8 plus 10 plus 12 is 42. This sum comes out to be 42. And one more here. Why don't you pause this and try this one on your own? Pause this and try this on your own. So the first number I'm plugging in is a 0, 2 to the 0. And then I just keep increasing I keep taking another step up the stairs until I get to 4. Into this formula, 2 squared, 2 cubed, 2 to the 4th. So 1 plus 2 plus 4 plus 8 plus 16. That's what I'm finding the sum of here. And you end up getting 31. That sum equals 31. So that's how sigma notation works. Sigma notation works by just taking that lower bound, plugging it in, and then calculating whatever expression you get in the end. So let's work backwards now. I'm going to give you a sequence, and I want you to tell me what the formula is. How do I represent it in sigma notation? So 3, 9, 16, 25 plus ... means the pattern keeps going all the way up to 100. Well, what are the other numbers in this ... is kind of our question. 36 would be there, 49, 64, 81. What are all these numbers here? Oh, these are all my perfect squares. So wait a minute. I'm going to find the sum and take a second and practice drawing a sigma of, let's do n squared. Aren't these all perfect squares? Where we're going to start at 3, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, all the way up until 10. That's what this expression is really the same as. We're adding up perfect squares starting at 3 and going till 10. I know it's tough, but I just need you guys to understand what this sigma notation is representing. Over here, looking at this pattern, -6, -3, 0, 3, 6, 9, 12, 15. So it looks like it's an arithmetic sequence. Isn't this an arithmetic sequence here? So we're finding the sum of -6, common difference of 3 times n minus 1. We're starting with the first term. First, second, third, fourth, fifth, sixth, seventh, eighth, and we're stopping at the 8th term. That's how I can represent that series using sigma notation there. Start at -6, keep adding 3, n minus 1 times. So noticing if it's arithmetic or geometric is extremely helpful here. 1/25, 1/5, plus 1, plus 5. The pattern here, it looks like it keeps doing times 5. Times 5, and then that brings me there. So this is a geometric series. This is a geometric series. Why? Because I keep multiplying. So I'm finding the sum. It's a bad sigma. I'm finding the sum of, well, what's the explicit formula? A1 r to the n minus 1. I'm starting at n equals 1. 1, 2, 3, 4, 5, 6, 7. It's 7 terms in that I have to get to tell me where to stop. So I just counted up my terms to see how many I needed until I stopped. Here we've got x squared, x to the 3rd, x to the 4th, x to the 5th, x to the 6th. So it looks like we're indexing that exponent there, right? We're starting with n to the 1, n to the 2, n to the 3, n to the 4, n to the 5, n to the 6, all the way up until n. That represents, sorry, I made a mistake there, my fault. Notice I used the letter I. Actually, I is a bad letter to use. Let's use K. Why is I bad? I is our imaginary unit. Let's use K. K equals 1. Start with K equals 1, K equals 2, K equals 3, all the way up until K equals n. Why can't my letters look nice? X to the K. There we go. So I'm starting by plugging in a 1 for K, and then I'm going to work my way all the way up until I get to the nth term in that sequence. So I know this series stuff is tough. Luckily, New York State doesn't ask us a lot about this working backwards, where here's the sum, give me the sigma notation. A lot of the times it's just plugging in and being able to interpret it. We're going to skip number 3. And let's jump. Actually, let's call it a day there. Let's call it a lesson there. I'm going to not focus mainly on this because what comes after this is the really important stuff. In next week's lessons, where we look at geometric series in particular, are going to be important. I just want you guys feeling comfortable with this sigma notation, that you know how it works. So I need you guys to understand that this sigma here means find the sum. The lower bound is the starting number you plug in. This is the last number you plug in, and you plug it into whatever formula is sitting next to that sigma there. So I'll give you a couple of practice problems with this. Try the homework. Let me just double check that the homework's good before I send you off. Yeah, the homework's not bad. Try the homework, and then do the problem set that relates to recursive sequences, sequences in general, and some series work. See you guys in the next video.